Welcome to a new episode of the Frontier AI podcast on YouTube, The Distributed Core. I'm your host, Krish, and in this episode, we analyze the complex architectures and mathematical frameworks powering today's AI revolution. Today, we are moving beyond the physical server racks to explore the mathematical foundations and algorithmic optimizations that make training trillion parameter models possible. While the hardware provides the raw floating point operations, it is the mathematical orchestration of parallelism and memory hierarchies that determines whether a training run succeeds or fails due to the GPU memory wall. Now let's look at the crisis of scale, the mathematics of attention. At the heart of every large language model is the attention mechanism, a mathematical process that allows the model to dynamically weigh the importance of different tokens in a sequence. This process uses query, key, and value vectors to determine how much one part of a sentence should attend to another. Mathematically, however, this is a double-edged sword. Standard self-attention exhibits quadratic computational complexity and memory consumption relative to the sequence length. As we scale to longer context windows, this quadratic growth becomes unsustainable for high bandwidth memory. To solve this, researchers have developed memory-efficient attention algorithms. These prove that self-attention can be calculated with logarithmic memory complexity rather than quadratic complexity. This is achieved through a technique called lazy softmax, where the normalization factors are tracked incrementally, allowing the final division to be delayed to the end of the operation and reducing the need to store massive intermediate matrices. The geometry of parallelism, 3D parallel strategies. When a model's state, the sum of its parameters, gradients, and optimizer states exceeds the memory of a single device, we must partition the mathematical graph. This is known as 3D parallelism, which combines data, tensor, and pipeline parallel strategies. Data parallelism partitions the training data along the batch dimension. Each device processes a different segment of data, and gradients are aggregated across the cluster. To optimize this, the Zero Redundancy Optimizer Zero was developed. Standard data parallelism is mathematically wasteful because every processor holds a redundant copy of the model state. Zero 3 eliminates this by sharding all model states across every device in the data parallel group. This reduces memory consumption linearly with the number of processors, allowing a trillion parameter model that requires 20 terabytes of memory to be distributed effectively. Tensor parallelism slices weight tensors within each individual layer. For a standard transformer layer, the weight matrices are split along row or column dimensions. This allows partial results to be computed independently on different processors before being aggregated via collective communication. Pipeline parallelism partitions the model vertically by layers. The model is split into stages, and input data is divided into micro-batches that flow through the pipeline. The mathematical challenge here is the pipeline bubble, which represents the fraction of idle time when processors are waiting for data from the previous stage. To maximize efficiency, we must saturate the pipeline by ensuring the number of micro-batches significantly exceeds the number of stages. If you are enjoying the podcast so far, please like and subscribe. Now let's look at the optimization algebra and the craft of tiling and mixed precision. Global parallelism is only half the battle. We also need kernel-level optimizations. Flash attention is a primary example of an I/O-aware tiling algorithm. By partitioning large matrices into smaller blocks that fit into fast on-chip memory, it reduces the frequency of slow reads and writes to global memory. This essentially fuses matrix multiplication and normalization into a single operation, increasing arithmetic intensity. the ratio of computation to memory movement. We further optimize through mixed precision training by performing forward and backward passes in 16-bit formats like FP16 or BF16. We halve the memory required for activations and gradients compared to standard 32-bit formats. BF16 is particularly favored for language models because it maintains a wider dynamic range, preventing numerical instability when gradients become very small. Newer architectures are even pushing toward FP8, utilizing different bit configurations for exponents and mantisas in different phases of training to balance range and precision. How does the power of scaling laws matter? Why go through this mathematical rigor? The answer lies in neural scaling laws. These empirical observations show that model performance scales predictably with the size of the dataset, the number of parameters, and the total compute budget. Currently, the consensus suggests that a model can continue learning effectively up to 20 to 200 times its parameter count in training tokens. For a trillion parameter model, this means processing trillions of tokens, requiring roughly 120 million exaflops of total computation. This plot thickens at the infrastructure backbone level. None of these mathematical operations can be executed without a specialized interconnect. Inside a single server, NVLink provides high bandwidth, fully connected or mesh topologies for the frequent communications required by tensor parallelism. However, for communication between nodes, we face the bottleneck of network latency. We rely on technologies like InfiniBand or RoCE, RDMA over Converged Ethernet. These use remote direct memory access to let one processor access another's memory without involving the operating system, which is critical for the synchronous barriers of distributed training. On massive systems like Frontier, which uses hundreds of thousands of cores, this requires custom network providers and software stacks to ensure communication stability across the entire fabric. Now let's summarize. Training at the scale of 175 billion or 1 trillion parameters is a massive distributed optimization problem. It requires balancing the quadratic complexity of attention with logarithmic memory optimizations, sharding model states across thousands of devices, and managing pipeline bubbles with surgical precision. The supercomputers we use are merely the canvases upon which this mathematical symphony is performed. Thank you for joining me for this technical dive into the core of LLM training. Next time, we'll examine a new topic in Frontier AI. But until then, stay tuned.